connectivity for external networks on the overlay, and Gregory A. Smith from Nutanix will be presenting.
Thank you, Ben. So we're going to try and speed through this because there's a lot of material. I'm going to talk about external networks on the overlay, and to start with, we're going to talk about why you'd want to do something crazy like that. So typically, you have external connectivity bridged to your overlay networks through a gateway node. You program some NAT rules in OVS. You have these localnet ports that Mike just talked about, which take care of bridging your NATed traffic to the physical VLAN. In our case, our gateway doesn't speak OpenFlow. So we can tunnel traffic to it, we can configure it through netconf, but it's not an efficient enough configuration interface for us to be programming NAT rules all the time as floating IPs and VPCs come and go. So what we would prefer is to split up the gateway and have an OpenFlow controlled gateway, which is where we're handling all of our NAT for floating IP and SNAT, and then tunnel the NATed traffic to our physical gateway, which will take care of bridging it down to the physical network. So in the logical topology, it looks something like this. You have the orange and green networks corresponding to the tenants overlay, and then this blue network, which is all of the external overlay network. Each tenant router connects to an external subnet, and that's bridged via a logical router to a logical switch port corresponding to our physical gateway. And in the southbound database, we bind that logical switch port to a chassis whose encapsulation defines how we're going to tunnel NATed traffic. So this works fine for north-south, no problems there. The issue is in east-west, and that's what the rest of my talk is going to be about. So I'm sorry about the tech side on this slide. There was a lot of information. I didn't know how better to do it. But basically, you can think of this as kind of being like the southbound database. You've got data paths and ports and patch ports. At the bottom, you have your chassis. Our two tenant networks are still in orange and green on the right and left, and the external network is in the center. We're going to demonstrate a ping from the green port private IP on the extreme left to a public IP that's been assigned to the orange port on the extreme right. This starts all on chassis 1. I'm going to fade out the areas of the data path that are not rendered in chassis 1's local tables. Here goes your ICMP request. It makes it to the tenant router. And the tenant router doesn't know the MAC address for this public IP address. So in order to learn the MAC binding, it sends out an ARP request. The ARP request has to go via the chassis redirect port. So we tunnel to chassis number 2. Out goes the ARP request. It gets bounced over to the external subnet, broadcast, and that's unfortunately the end of this story. There's no ARP responder on chassis number 2 for this floating IP. So going back to more familiar architecture for folks that have worked in OVN, you would expect that this ARP request would actually go out via a localnet port to a physical network where it would be flooded by a physical switch to all of the chassis on that public network. And so, of course, you would have an ARP responder on one of those chassis that finally gives you your ARP response, and that's how connectivity is achieved. For ourselves, we worked around this problem using L3 gateway ports. So L3 gateway ports are a lot like patch ports, except that you have the ability to bind them to a particular chassis. So if we use centralized NAT, which means that all of your floating IP traffic flows through the tenant's chassis redirect, the chassis that's been used for the chassis redirect port for that tenant's virtual router, we can just bind the L3 gateway port to that same node, and then we have an ARP responder there. So going back to our diagram here, we've got the ARP request. It's the external subnet. We're going to gray out the stuff that's not there. You're going to notice now that unlike before, because we have these L3 gateway ports, there's no longer full connectivity between the tenant networks. And this is actually kind of a nice property that came out of this hack. So now the ARP request gets forwarded, tunneled over to chassis number 3, and finally we have an ARP responder that can make the response. I'm not going to go through the ICMP path, but it's basically the same idea. So the trade-offs here, this works fine for floating IP to floating IP or SNAT to floating IP. Provides that nice isolation, like I said before. It required only really minor changes to North D and networking OVN. but it has some major trade-offs. So it doesn't work with distributed NAT, which is a huge loss. There's really no reason we should be forwarding all of our floating IP traffic through a centralized node. It doesn't work nicely with gateway HA. So gateway HA is where you define a group of chassis that can all function as a gateway, and they decide dynamically using BFD which one of them will actually be the gateway. It makes it difficult for us to figure out which one we're supposed to bind to. But the most galling part is really that it still relies on ARP. And the fact that we're ARPing to resolve the MAC binding for a floating IP that we programmed just seems fundamentally wrong. So in closing, basically I want to know if anyone else is interested in splitting the gateway in this way, or if we're just doing something crazy. And if other people are interested, what's a better way to do this? Because the L3 gateway thing is obviously a hack.
Great questions. Let's give our speaker a round of applause here.
Thanks, folks.